Greetings, I'm Alfonso Pineda, and welcome to another lecture from the 2020 Honors Chemistry Short Lecture Series. Have you ever heard about nanomaterials? You probably haven't, so you may be asking yourself, what are nanomaterials? Well, if you find yourself asking that question, or you haven't heard about them and you are intrigued by these mysterious nanomaterials, today's your lucky day. Today, I will be talking about nanomaterials, what they are, several examples of them, and how they may be used in several different applications. These particles may be small, but they sure do look like they have a big future ahead of them.
Okay, so let's begin. First of all, here's the outline of my presentation. I will start off by summarizing my inspiring article, which talks about the relatively new use of gold, a normally unreactive transition metal, as a catalyst when engineered into a nanomaterial. Then we will go into the detail of what are nanomaterials and what exactly classifies a nanomaterial. Following that, we will touch on the different types of nanomaterials and several examples of the different types. Then we will explore more fully the main topic of my inspiring article by seeing why nanomaterials make excellent catalysts even if their bulk form is not reactive at all, and how they may be more effective than other catalysts. Afterwards, we will see how a different type of nanomaterial can be used to find tumors effectively. Following that, we will see a potential application of nanomaterials which is very relevant to today's events. I will then address possible safety concerns related to working with nanomaterials. Finally, I will conclude with my final thoughts about the potentially bright future and pros and cons of the use of nanomaterials in these applications I specified. My CNEN inspiring article was called Zeroing In on Golden Mechanisms and was written by Mitch Jacoby. This article basically talks about how not too long ago gold was thought to be chemically inert. Now scientists have discovered that by engineering gold into tiny particles around 2 nanometers in diameter, gold's properties change and it has the potential to become an excellent catalyst. The scientists also talk about the process that the gold goes through to become an effective catalyst. For example, on the right, we can see two different examples of gold being used as a catalyst. The scientists explain how exposing gold to ozone is what helps form the formation of the uniform nanoparticles. Without oxygen, the gold could be prone to clumping up together and therefore could lose some of its newly gained abilities. From here on out, scientists may treat the gold surface to expect a specific reaction. In the instance of the picture to the bottom right, it shows how scientists were able to catalyze the reaction of benzene acetaldehyde with methoxy intermediates to form their desired product, methyl ester. Overall, this article inspired me to look more into the world of nanomaterials and their applications not only as catalysts, but as much more. Now I will talk about what exactly makes something be defined as a nanomaterial. Basically, the material particle size must be in the nanoscale, and if you remember your SI prefixes, you'll know that nano corresponds to 10 to the negative 9th power. This means that the size of the material's particle usually is within the range of 1 nanometer to 100 nanometers. That would make the particles equivalent to around 1 billionth of a meter. Now we will get to their properties. So obviously nanomaterials are very small, and just like how the CNDN article said, some of them, like gold, are good catalysts. However, there are also other types of nanomaterials. For example, carbon nanotubes, which are allotropes of carbon, can be used in several different nanotechnological applications, or benzene, which is the molecule C6H6, which can be used in developing adhesives, paints, tires, and more. Another example of nanomaterials are quantum dots, but I will expand on these further in a future slide. Now I will go over the types of nanomaterials classified into engineered, natural, and incidental nanomaterials. So on this slide, we see images of nanotubes, which are engineered nanomaterials. This means they are specifically man-made by scientists for a specific purpose. This would include the gold nanoparticles that were discussed in the CNEN article. Carbon nanotubes are generally used in more nanotechnological based applications, but it is a nanomaterial nonetheless. We also see a Buckminster fullerene, otherwise known as a buckyball, which we did address in class to be an allotrope of carbon. The buckyball is an engineered nanomaterial, but it can also be found naturally in ash and soot. For an example of natural nanomaterials, we have volcanic ash. In this volcanic ash, we can find different naturally occurring nanomaterials and nanoparticles. On the right, we have a diesel engine to represent the combustion of diesel. Now, even though they may not be desired, Nanomaterials are a byproduct of the combustion reaction. These are the three main types of nanomaterials. Now we will go deeper into what makes nanomaterials good catalysts. One of the main reasons they are such good catalysts is because they have a small volume but large surface area. A large surface area benefits reactions. You may be thinking, how does it have a large surface area if it's so small? The figure on the right shows how as the shape, in this example cube, gets smaller, the surface area to volume ratio increases. Nanomaterials are also good catalysts because they provide increased selectivity. More precise ratios of reactions can be used. Using these small particles also proves to be quite cost efficient compared to other methods, which is a good thing. One application of how they could be used actually helps eliminate pollution. Nanomaterials could be used in automobile catalytic converters or in power generation equipment to react with toxic gases such as nitrogen oxide or carbon monoxide, and environmental pollution could be avoided when fuels are burned this way. Another application for nanomaterials comes to us in the form of quantum dots. These quantum dots have helped advance techniques in vivo imaging and could even help detect cancerous tumors. In the picture below, labeled A, we can see how the cancer cells can be tracked in vivo with quantum dot imaging. Using quantum dots also provides the advantage that images can be recorded for a longer amount of time because of the resistance to photobleaching compared to other materials used in imaging such as proteins or fluorescent dyes. It is also noted that by manipulating the size of the quantum dot, they release a different wavelength of light when energy is being released. This could prove to be useful not only in this application, but also in other ones. One example of this being used is QLED TVs, but I won't get too much into that. Another application for nanomaterials is that they also have the power to help stop the spread of diseases or viruses, which could prove to be a very useful application, especially during the current times. Fairly recently, scientists have noticed how nanomaterials may help stop the spread of viruses. In 2010, a 2-year program in the UK dedicated $3.5 million to research specifically for this application. However, that is not all the research that has gone into this field. Our research in 2015 helped show how nanomaterial nanofibers could be used in gauze masks. This would make them more effective and more breathable. An earlier study in 2006 also helped to show how by using certain nanomaterials, nanoparticle-coated fabrics could help stop infectious agents from spreading. Overall, nanomaterials could prove to be a useful ally in helping return our life to normal faster during these times. However, no matter how exciting nanomaterial applications may prove to be, we should first look at the safety and we should focus on that so that things don't go wrong. In my opinion, there should be more research going to figuring out which nanomaterials are the most safe or most dangerous to be around or accidentally inhale. Several studies over time have shown that nanomaterials may be carcinogenic or may cause several health concerns. As a result, people working with nanomaterials should learn the basics of safety around these potentially dangerous carcinogens. For example, a safety measure imposed on people working with nanomaterials is to minimize the amount of airborne nanoparticles by housing them in solutions so that they can't easily become airborne and therefore they can't be easily inhaled. Another simple but effective safety routine is to wear personal protective equipment around nanomaterials. Potential health effects could include, like I previously mentioned, carcinogenicity or lung inflammation, or even if just inhaled, they could cause both of these things. Overall, we should make sure the science is safe before we fully conduct it, in my opinion. Now moving on to my conclusion. Overall, I do think that nanomaterials do have the potential to have a bright future. For me, the pros definitely outweigh the cons, especially if we are careful and safe when working around these nanomaterials. So, it turns out these little particles may actually have a big future. And these are the works I used during my research.